All right, the last thing we have to talk about is continuous objects, okay? So when we say continuous object, it's like maybe like a bar or like a rod or something. But let's suppose that this rod does not have a uniform density. That means that maybe, like, for example, here the rod gets more dense as it goes, okay? So that means that the rod maybe doesn't have the same mass throughout, right? Maybe the left side has more mass than the right side, right? And so obviously that's going to change where the center of mass is. Typically, the center of mass would be dead center, but here it's not going to be, okay? So there's an easy three-step method to figuring out, like, for example, if we have something that has, like, density varying, we can find the center of mass easily by splitting the object, okay, into tiny pieces that we were going to call DM. Now I don't know what that is, okay? I don't know what DM is, okay? But we're going to split we're going to split into these little tiny pieces of DM, okay? Then we're going to multiply. Do you see where I'm going with this? We're going to multiply all their positions, okay, by the DM. Okay, so we're getting the mass of each piece and multiplying it by its position along the object. Okay, that's going to give me x times dm. Okay, hopefully you see where I'm going with this, right? Then all we got to do is add them all up. Add it all up. Okay, and by that, what do we mean? I mean to integrate. Okay, you can integrate, that's fine. Okay. Okay, suppose that the center of mass of an object, right? So this is an integral version of the center of mass of an object that does not have uniform density. Okay, you do need to know that, right? So there's two definitions, right? This is the integral version, the calculus version. Now there's another version of this equation that I can show you, right? If I take the center of mass and let's say I want to multiply the whole thing by 1. If I multiply both sides by 1, I'll multiply x sub cm by 1. Okay, it doesn't matter. But on the other side, what if I want to multiply, maybe by like dx over dx, right? I can do dx over dx on the top, dx over the dx on the bottom. And you're going to see something kind of crazy happen. If I take the integral here, I get x times dm over dx times dx over integral of dm over dx. Okay? Dot dx. Okay? Wait a minute. M over x, right? M over x. Okay? M over x is actually density. Okay? It's actually density. Okay? Because it's the mass, right? The mass per length, right? So this is density. Okay? So another way to write this equation is to do x sub cm would be equal to the integral of x density of x, okay, the density function times dx, okay, over the integral of density with respect or density the density function dx, okay, and this part on the bottom is just going to get us the total mass, right? Because if density is dm over dx, right, then it's going to end up canceling out, right? Okay. Um, and now let's suppose, right, if we have a rod of length L whose density varies as a function of position according to the function, there's our function A root x is our density function. X is the distance from the left end of the rod. A is constant. Find the distance between the left end of the rod and the center of the mass. Okay, so we need to do so we've got a top integral and a bottom integral, and then we can combine them. So I'm going to solve it piece by piece here. To find the first moment of mass, which is the top integral, okay, I just got to do, let's see, from L to 0, or from 0 to L, okay, of x dot a root x, okay, dx. Okay, great, that's all fine and dandy. Now, I'm going to rewrite this in a form that's going to make a little bit more sense to me and easier to integrate, okay? L, from 0 to L, x, this has an exponent of 1. Okay, I'm just going to write that there. You don't have to write that if you know that, but I'm going to write that for myself, okay? Times a times x to the 1/2, okay, dx. I like having all of my my I like having all of my exponents visible, okay? And I should be able to see, okay, I can actually multiply these together, okay, to get x to the 3 halves, or sorry, ax to the 3 halves, okay, dx, okay, okay. And then when you integrate this, you're going to end up getting something, you should end up getting 2/5 ax 5 halves, ax to the 5 halves from L to 0, or from 0 to L, okay? So this is not the final part because we have to apply our bounds now. And when you apply the 0, the whole thing's just going to become 0. So you just have to do the L part, which is 2/5 a L to the 5 halves, okay? Okay, that's the top integral. Let's do the bottom integral, okay? Again, it's just a root x, okay, dx, okay? All we got to do there, okay? Then we do L from 0 to L. We're going to do ax to the 1/2 just to make it easier for me to see when I integrate. And when you integrate it, you should just get 2/3 ax to the 3 halves, okay? And that's going to go from 0 to L. And again, the 0 part's just going to be 0. So you get 2/3 al 3 halves, okay? Beautiful, wonderful, I love it, okay? Very happy about it, okay? Then to find the location of the center of mass, all I got to do is put everything together. So the top integral goes in the top, 2/5 al 5 halves over the bottom integral, 2/3 al 3 halves, okay? Al to the 3 halves. And what you should notice, right, first off, right off the bat, get out of here, A. Okay, A's are gone, okay? Um, the 2/5, so really this is the same thing as saying 2/5 times 3 halves. And then the L's here can actually subtract because they're being divided. You remember your exponent subtraction rules from like algebra 2? Okay. You'll actually end up getting, this will be just actually just L. Okay. And when you multiply these together, you end up getting that the position of the center of mass should be about 3/5 along the length. Okay. Now that's specifically for that density function, right? That's not going to work for everything, but if you have something with that density function, that's how you get it, okay? All right, that is all for center of mass. Okay, when we pick up next time when I come back, we're gonna do we're gonna actually start with like the momentum stuff. Okay, so yeah, live, laugh, lab. Okay, bye.